Welcome to Integrated Math 3. On this episode, Stevenson will demonstrate
Let's look at another example. So remember, our first step is to try to simplify our our rational where we can. So the first thing I'm going to recognize is my quadratic in the denominator is factorable. Now I'm going to simplify and rewrite. So now I can see what's left over. Now whatever's left over in the denominator will represent your vertical asymptote. So I can see my vertical asymptote is positive 1. My end behavior asymptote, well, let's look at the degrees. My denominator's degree is bigger than my numerator's degree, so my denominator's going to grow faster. Therefore, my end behavior is the x-axis, or the line y equals 0. Next, let's figure out if this has a hole. Well, remember, a hole exists, or in other words, the removable discontinuity exists when a quantity simplifies. Well, there was a quantity that simplified here. So what we're going to do is we're going to take whatever simplified. In this case, it was x minus 3. We're going to set that equal to 0 and solve. Now I know where my hole is, or when it exists. It exists when x equals 3. So I can see again I have two domain restrictions. I have a vertical asymptote at 1 and a hole at 3. Now let's do our sketch. So I start by doing my vertical asymptote, which is positive 1. Next, I'm going to graph my two pieces. Because there's no reflection, I know my pieces are going to exist roughly here and here. However, the hole will exist at 3. So I'm going to put a little marker at 3 and know my hole will exist somewhere in there. Now let's do the domain. So in order to do the domain, we like to do a little sketch. So we're going to mark the exceptions to our graph here. So the exceptions are, positive 1 and positive 3. So I cannot have 1 or 3, but I can have everything else in between. So now let's write out the domain. Let's write it down in words. We would say all real numbers except x equaling 1 and 3. Now let's check our graph and see how we did compared to Desmos. There we can see the vertical asymptote there. Now the hole was at 3, so 1, 2, 3, so it should be somewhere right here. There it is. There it is. Very cool. Let's look at one more. In this example here, hopefully you recognize this is a little different. We basically have the same quantity on top and bottom. So when this simplifies, I'm just left with 1. So graphically, this is really simple to do. This is just a horizontal line that goes to the y-axis at 1. However, because we know this is a rational function from the beginning, this means because they simplified out, we're going to have a removable discontinuity. In other words, a hole. So let's get to work. When I look and see here, and I realize there's no variables left, what this tells me is there's no vertical asymptotes. The end behavior asymptote, well, do you see how the degrees are the same? The degrees are exactly the same, so we're going to divide the coefficients. So this is 1 over 1, so this means the end behavior is y equals 1. Let's look for the removable discontinuity, the hole. So we're going to take what it is that we simplified, and we set that to 0 and solve. So this means there's a hole when x is negative 3. Let's go ahead and do our graph. So basically what we're going to have is a horizontal line through 1, but it'll have a hole when x equals negative 3. Let's go ahead and find our domain. So let's figure out our domain. If we were to describe this, we would say all real numbers except x equals -3. Let's check our graph. So there's no vertical asymptotes here, but you can see it's just a constant line through 1. See, there's 1. And we were supposed to have a hole at -3. So let's go over here to -3. Oh, there it is. There's the hole. So just to recap, removable discontinuities or holes exist when your quantity simplifies in your rational function. Whatever's left over in your rational function in the denominator becomes your vertical asymptotes.